Welcome back. We are going to proceed with our little diversion from our diversion. Like the whole study of geometric algebra is this diversion we've taken from QED prerequisites. And inside the paper we've been reviewing, we're diverting just a little bit to talk about relativistic physics inside the space-time algebra system. And we got warmed up last time, and this time we are going to proceed with some examples. So let's begin. So the first example that Duran and Lazenby, is it Lazenby? Yes, Duran and Lazenby offer up is the notion of understanding velocity in the space-time algebra. So they write, suppose an observer with constant velocity v measures the relative velocity of a particle with the proper velocity u of tau, where u squared equals 1. All right, so that setup alone is worth thinking about. A lot of the trouble sometimes that I've had learning this is understanding how people are setting up, or how different authors are setting up the situation. And typically in special relativity, you spend a lot of time with diagrams showing the setup. But here, they feel like you're comfortable enough with the language, you don't need to see the setup. So let's see if we can unpack this setup a little bit. Now, when thinking about the setup, I'm very inclined to go back to a different section of the same paper where they talked about relative vectors. And they said, suppose we are an observer in some inertial frame. Well, an inertial frame is a frame moving at a constant velocity v. Our velocity is v. The inertial frame is generated by the unit time-like vector v and the frame of rest vectors perpendicular to v. So therefore they described E0 is defined as v. And if that were the case, then it would be very logical, let me see if I can find my rest frame, to think about the setup in this terms, right? We just erect our frame of reference where the time-like orthogonal basis element vector is defined as v, right? Draw this little neater here, right? We simply define this as v, E0 is v, and we might give us a spatial vector here, and this path is x of tau, and anywhere along this path, the velocity is given by u of tau. So this is x of tau here, right? X of tau is this thing, and then u of tau is that derivative with respect to proper time. That might be a reasonable way to set it up based on the way this paper is kind of written. However, there is another way of looking at this. And that is, we say, no, the observer has a velocity of, or a geometric space-time algebra defined velocity, v. This is its world line, right? This is the, let's see, how do I describe this, right? This is the world line. This green line here is the world line of the observer. And that world line's velocity is constant velocity v. And it's this observer that's observing this particle here, this particle moving at, with world line x. And we're interested in the quantities between these two. It's very much like in standard special relativity, you would call this velocity addition, right? So it's a little unclear in their paper about how they're setting up this section on, this section on velocity. Are you using it the first way or the second? It turns out it's the second of the two, right? There is some observer with constant velocity v, and they're speaking in great generality here. Now, it could very well be that the spatial part of this constant velocity v, right? So this velocity v would have to be, remember, v0, e0 plus v1, e1. Let's just say it's those two. Let's say it's got no component in e2 and e3, right? It could very well be that v1 equals 0 and it's stationary, right? But it doesn't have to be, right? It could actually just be in this full form. And all of these expressions here will still be true, which is kind of really, really nice. You sort of get velocity addition built right into this process. So for the purposes of our setup, we will set it up using not this, right? We won't use this. We'll just say that this is some E0. I better do it in black, I guess. This is some E0. This is some E1. And the velocity of our observer is some velocity v, and the velocity of the particle is some velocity u, right? And with that, well, we start formulating this geometric product. First of all, u, of course, u squared is 1. This is the proper time. U is the proper time. So it's very important to understand that u is the proper time derivative of x, because that's the first thing they do here, right? They say uv, the geometric product of the two space-time algebra vectors, u and v, right? That is going to be, well, u is defined as d tau of x of tau, right? Well, that's exactly what this is. V is a constant, right? V is a constant, so the product rule applied gives you a 0 for the second term, so that's nice. And then they take this idea that we know how the geometric product of x with a velocity is. We know that gives you t plus the relative. T is the coordinate time plus this relative vector. And this coordinate time t is a real number, or a blade 0 object, and this is a blade 2 object, which is the relative position vector. And we know that from our previous work right here with relative vectors, where they work this out. With these definitions, xv is t plus relative vector x, because that's going to be a number, which is t, and this is going to be the relative vector x. And then they showed you this nice decomposition where x squared is always t squared minus x squared, which is cool. Okay, so back to our work here. So now we also know that this has to equal u dot v plus u wedge v. And because of that, we can now equate this term, the scalar term, with t, right? And, I'm sorry, not with t, right? But with d tau dt, right? So that gives us this expression, d tau dt equals u dot v. Now, with my sensibility about special relativity, I immediately know that this is gamma, right? Because gamma, meaning the space-time factor gamma, because I know that gamma is the coordinate time versus the proper time. So this thing is gamma. And u wedge v is all that's left over. That must be the partial derivative of the relative vector, the partial derivative with respect to proper time of this relative vector, which is u wedge v. So now they say, well, what I want to know is the relative velocity, which means I want to know how fast is the relative vector changing with respect to coordinate time. And now this coordinate time is the coordinate time of v, right? V's coordinate time. Because it's, when you break this up here, this dot product is u dot v, not u dot e0. It's u dot v. So it's the coordinate time relative to this observer. And to get that, you just do a little bit of calculus, and you multiply, you know what dx d tau is, because dx d tau is u wedge v. So we know what this guy is, right? We know dx d tau, and we know dt d tau, so we take its reciprocal, and since d tau dt is going to be 1 over u dot v, because we know dt d tau is u dot v, right? So then we just form this factor, or this fraction, and we get our answer for the relative velocity of u with respect to v, right? It's u wedge v over u dot v. And this is pretty elegant, right? This is a pretty tricky thing, right? If you think about what we've done, we've actually said, okay, we have one object moving at velocity v and another object moving at a velocity u. Kind of forget the frame we're sitting in. We don't need to worry. We never did any reference to this frame. We just want to know, what does v interpret u's velocity as? Well, we understand that that's going to be the spatial motion of well, I got to call this object B, right? The spatial motion of object B, and the observer is A, right? The spatial motion of object B, its spatial velocity, if you're observer A, is going to be this guy U, and that guy U has got to be partial of x of tau with respect to t, where t is the coordinate time of v. And that it just comes a lot easier than velocity addition would from regular special relativity. So that's kind of nice. So let me erase everything here. So this expression is pretty sweet, because we can calculate these things relatively easily in space-time algebra. So what their next, so this is the answer to the question, by the way. Suppose the observer with constant velocity v measures the relative velocity of a particle with proper velocity u of t. So when I say measures the relative velocity, that means v is wondering, if you were v, how fast would you see this guy moving in your spatial frame of reference? That's what this problem is asking. And the answer is, well, it's position in your spatial frame of reference divided by your coordinate time in your spatial frame of reference. And that's what this answer is. So then they do something here. I don't quite understand why they do this paragraph. I've already identified gamma right here. As soon as I saw dt d tau, I said, oh, that's gamma, cool. Gamma's just right there. But they're saying, no, we got to now form the Lorentz factor gamma. And so the way they do it is they say, well, if you're V, right, if you're, I guess, observer A, the way I've called it now, you see the guy moving with velocity u, this relative velocity vector u. And so, well, gamma is, by definition, 1 over the square root of 1 minus the velocity u squared, right? That's equal to gamma. That's by definition, that's what we call gamma. So they write that down this way here, right? They're expecting this square to give us a number, and this will be 1 over gamma squared. So then they execute this calculation to determine that, and what they're trying to show is that gamma to the minus 2 is u dot v to the minus 2, and therefore gamma is u dot v. But u dot v this is gamma here, right? They're doing a lot of work to show you that gamma is dt d tau, I guess. But I already know that just from special relativity. So I was done with this step up here. But they feel the need to sort of walk through it. It is worth walking through to see how this calculation goes. So let's go through this calculation and calculate their version of 1 over gamma squared to make sure we understand how the calculation works. Okay, so let's take a close look at this calculation. There's calculating 1 minus the square of the relative velocity vector. So step 1 is we substitute for the relative velocity vector our new understanding that it is the wedge product of the actual velocity vectors, right? This is a relative vector, so this is, this is written in the E1, E0, E1, E0 basis in our particular problem. But that, although it's in the space-time algebra, that's a bivector, we look at it now, we kind of think of it as the regular vector that we would have known from regular physics. But what we do is we replace it with this substitution that we just did the calculation of, and then we're going to blow this guy up using the space-time algebra. So we take note that u wedge v times u wedge v, right? That's u wedge v squared. And we could leave it like that. But what they do, and I'm duplicating exactly the process that they used in the paper, in Doran's paper, they actually switch u and v in the second one, right? They switch u and v here, and they make it v wedge u, and then they bring out this minus sign, right? And that's going to make it a little bit easier to do the calculation in a moment, as we'll see in a second. But we make this substitution in here for this u wedge v squared, and then then they use the fact that u wedge v equals the geometric product of u and v minus u dot v, right? That is just, using the fact that the geometric product is u dot v plus u wedge v, right? So you make that substitution. And so this u wedge v right here becomes this thing, and this v wedge u becomes this thing. And that's how they end up with this first line. And of course, the minus sign from that flip ends up right here. It comes out. And the denominator is just a number. U dot v is just a number. So that's number squared. We just pull that out front. And so now we just have to expand this using our geometric algebra techniques. Everything distributes, so we just get uv vu for this first term. And that's why we did the swap, right? It's very easy because v squared is 1 and u squared is 1. So this is going to very quickly just become 1. So that's this term and this term together go there. Then you have this term, and that goes there. U dot v times vu. So it's this dot product times the geometric product. And then, of course, you have the reverse of it. You have this dot product times the reverse geometric product. Now, u dot v and v dot u are the same, right? It commutes. This dot product commutes because it's the symmetric part. So these two things come out front. These two minus signs come out front. And what you're left with is uv plus vu. But uv plus vu, well, u dot v equals 1/2 uv plus vu, right? So this is just equal to 2 u dot v, right? And that's how this whole thing ends up like that. Here's u dot v, here's u dot v. That's two factors of it. So there's the exponent. And this factor of 2 comes right from there. And then this last part just becomes u dot v squared. Okay, so the next step is to distribute in this piece, this 1 over u dot v squared, right? Just erase that and give it a better looking square. And so how does that next step look? So now bringing this guy in, bringing this guy into here, we get 1 over u dot v squared. And this is 2 u dot v squared, but that comes in here. So that's going to cancel right away. We can expect a cancellation right there. And then u dot v squared under u dot v squared is going to give you this 1. So you combine everything together, you get 1 plus 1 minus 2 plus 1 over u dot v squared, which is this expression right below. And now all this stuff cancels, of course, and you just end up with u dot v to the minus 2. So I guess ultimately I should be writing down, right, this is 1 minus u dot v, but that is equal to gamma to the minus 2. And see, you know this from special relativity, right? I mean, in special relativity, you know gamma equals 1 over the square root of 1 minus magnitude of u squared, right? You know that. So you immediately know how to create gamma to the minus 2 because you know this. Well, the thing that I knew was that dt by tau is equal to gamma, right? So you got to know something to connect this all together. Anyway, you get gamma to the minus 2. That all cancels, and from this you conclude that gamma equals u dot v, I suppose. Okay, so so we have demonstrated this formula right here. We've walked through it a little bit. That was good. That was worth doing. And then, of course, they just repeat what we just said, gamma equals u dot v. Okay, so what next? So the next line reads that it follows that we can decompose the velocity u as uvv, and we can do that because, remember, v squared equals 1. So we can always put a vv in these things. And when we do that, we end up with u dot v plus u wedge v. That's this first uv part, right? The first, this first uv is this piece right here, right? It's just the geometric product of u and v. But now that we know that u dot v is gamma, and now that we also know that u wedge v over u dot v, which now we can write u wedge v over gamma, we know that this is the definition of the relative velocity u. So because of that, we can write this form here in this form. And what we're supposed to take note of is that u can be split using this very easy form into u is gamma v plus gamma relative vector u v. And this is the component of the velocity u in the direction of the velocity v, sort of the time-like part. And this is the pure space-like movement or I should say space-like, but the pure spatial movement in the frame of v, right? And what's nice about this is true for any v, right? So this justifies going back to our choice of setup here. Remember, we said, okay, there's a guy velocity, there's somebody traveling at velocity v making an observation of object b, which is moving with velocity u, and that's respect to some arbitrary frame, right? E0, arbitrary frame E0, E1. And so we're sitting in this E0, E1 frame, and we're asking questions about how do we divide up this velocity as though we were sitting in this in the frame of A, right? And in many ways, that is very akin to an addition of velocities problem, right? In other words, we know the velocity of this observer v, and we know the velocity of this observer b, but we're asking, what does v think b's doing, right? And the way to do that is through this process right here, right? This is what v thinks b is doing, gamma uv. And we can test this. We can test this using a simple, I think I set it up here already. Let me just check. Yeah, just using the simplest possible thing. Let's say v is actually stationary. V is at rest, right? So that this line here, this line for A is just vertical. It's just going like this, right? Well, if that's the case, then u is just u0, e0, u1, e1, and uv is given by this formula that we just found. And we believe that the first part of the formula is going to give us this time-like part, but the second part is going to give us the relative velocity. So we can calculate this, right? We can calculate gamma, which is u dot v. Well, here's u, and this is v, and u dot v is, this part is going to be 0, and this part is going to be just u0. So that becomes, all that becomes u0. And then this becomes 1 plus, and then here's the relative stuff, right? This is u wedge v divided by u dot v. Well, we know this part here in the denominator, this part is u0. We just figured that out. And this part, well, the first piece of the wedge product goes away because, no, this, because it's e0 wedge e0, so that's gone. But the second part is u1, e1 wedge e0. So that part goes right here. And then you just crunch a little more. We distribute this. We get UE0. And then we get U1 times E1, E0 times E0. Because we have this V here, right? This V is that E0, which is now that E0. And so we know how to calculate this from the work we've done previously. So we know that that's going to equal, let's see, it's going to equal E1 times E0 dot E0 minus E0 E1 dot E0, right? That's a formula that you should have memorized right now. The triple part, which would be E1 wedge E0 wedge E0, that goes to 0 because you have two E0s there, right? So you only have this vector piece. You don't have a trivector piece. And E1 dot E0, well, that is 0. So all you have left is this. And E0 dot E0 is 1. So you end up with U1, and all of that is just E1. And so this is our answer. Well, in this particular frame, that's not surprising. We've just discovered that it's already split into a purely space part and a purely time part. We just needed to show that gamma U relative V gave us that answer back. However, we could also do this with V being something more complicated and return to our condition where the path of A is not stationary in this sort of general reference frame that we're sitting in. And that becomes very similar to a velocity addition problem from classic elementary special relativity. And to show this, I think it's very instructive to show this in detail, even though Doran doesn't do it. Well, he does, but I'm going to actually do a real problem right now. So let's have a look. Okay, so I pulled this problem from a classic special relativity book. Right? You've got your spaceship, you've got your space station, and this spaceship has these guns that fire bullets. The spaceship, relative to the space station, is moving at 0.5 c, right? And it shoots a bullet, but it doesn't shoot it forward. It actually shoots it backwards. So let me redraw these guns. Hold on. Okay, there. So it has a rear-mounted turret, right? And what it's done is it's shooting this bullet here, right? It's shooting this bullet backwards. Now, it thinks, there, so it's not hitting its little tail there. So relative to the spaceship, this bullet is retreating from the spaceship at 0.75 c, and it's going backwards. So that's what that minus sign is for. And so we call this the U prime, the relative velocity vector of this bullet relative to the spaceship. So it's now in the prime frame, is minus 0.75 c. Relative to the space station, the spaceship is moving at 0.5 c. So it is a very routine problem of elementary special relativity to say, okay, if the spaceship thinks that this bullet is moving back at 0.75 the speed of light, and the space station thinks the spaceship is moving at 0.5 the speed of light, how fast does the bullet look like it's moving relative to the space station? If the space station was looking at this bullet, what would it see? And what's interesting about it, of course, is that in Newtonian mechanics, right, this would just be going to the left at 0.25 c, but that's not the answer, right? Right, 0.25 c, right? And so now the basic answer from the fundamental relativity would be U, the relative velocity with respect to the station, which is unprimed U, is going to equal V plus U prime, which would have been the Newtonian answer, right, divided by 1 plus V, or I guess V u, right? The product of the two. Now, here, notice that these are just numbers here, in the way the standard elementary version does it. It's just everything is one dimension, so you don't need these vectors. I haven't included a unit vector here, for example, but this would be E1, right? If we did do that, if we put it in here, it would be E1, and then this would also be E1, and this would also be E1. So it's the same unit vector everywhere. This formula, however, is just the absolute velocities formula, so I'm abusing notation a lot, but I want to drag in the 0.75 and the 0.5. When we do this calculation, we're going to get u is minus 0.4, and that's pretty straightforward, right? You're just going to get 0.5 minus 0.75 divided by 1 minus 0.75 times 0.5, which is going to equal minus 0.25 divided by... Okay, so I think I've prepared it all. Same problem. U is minus 0.4c. U prime is minus 0.75c. So what we're going to do is we were given U prime... we'll do it slightly differently, right? We're going to do it where we know V, right? We're in the space station, and we measure the speed of the spaceship V, right? And we measure the speed of the bullet, and we get minus 0.4c. Now the question we're going to ask, just to sort of toss it up a little bit, we're going to ask, well, what does the spaceship think this bullet is doing? And we better get an answer of 0.75, right? So we're going to take the givens as this and this, okay? So the first thing we can do is we want to create our 4 vectors, right? Because we believe that the answer is going to be u wedge v divided by u dot v, right? This is supposed to be equal to the relative velocity of this object as seen by v, right? You just take the 4 vector of v, you take the multivector representing v, which is just a blade 1 object, the multivector representing u, you wedge them, you divide by their dot, and that's supposed to be it. And it's supposed to be it for any frame. So in this frame, going back to here, right? This is the spaceship moving along v, and u, this is the bullet. Now, in our case, the bullet is a straight line, right? The bullet is now, instead of wandering around like that, the bullet's got something more like that going on, right? And we're asking, well, what does v see the velocity of the bullet as, right? That's the problem we're solving now. So with that, so we're trying to formulate this object right here. So we have a couple different ways to do it, but I first want to get v and I want to get u. So one way to do that is to take advantage of our Lorentz transformations that we learned, right? This means inverse hyperbolic tangent. This is hyperbolic cosine, that's hyperbolic sine. This is the inverse hyperbolic tangent. So we know that the rapidity of the bullet, right? The bullet is going at 0.4c. So the rapidity of the bullet is the inverse hyperbolic tangent of 0.4, which is 0.4236. I did that calculation. And that's the rapidity of the bullet in the space station. And you can calculate gamma. That's just the cosine, the hyperbolic cosine of the rapidity. It's 1.0911. And you can calculate beta times the Lorentz factor, and that's the hyperbolic sine of the rapidity, which is 0.4364. So then we can say, okay, well, u prime, to get the 4 vector u prime, right? The 4 vector u prime, we just take, wait a minute, I already screwed this up, didn't I? That's actually u, right? The 4 vector for u, because this is u, right? The 0.4 comes from u, so this is the rapidity of u, meaning it's the rapidity of the bullet as seen from the space station, right? And that's what we want, because we want to calculate u prime. We want to get an answer of 0.75. So now we calculate what u is. Well, the velocity u, it's just going to be the velocity of the stationary, just time-like vector sitting in the space station's frame, right? And we rotate it using a Lorentz transformation. And that Lorentz transformation is going to, we want it to be moving to the left, right? The u moves to the left. So we rotate it with minus alpha 2. So when we rotate it with minus alpha 2, normally the basic Lorentz vector is going to be, would be e to the alpha 2, e1, e0, if this object was moving this way. But if the object's moving this way, we're going to put a minus sign there. And so our reversion is going to be e to the alpha 2, e1, e0. And so this is supposed to be our reversion r, but it looks like, because it's going the opposite direction, it looks like our reversion. Anyway, but because e0 is in the plane of e1, e2, it's going to commute with the bivector e1, e2. Well, it's going to anti-commute with the bivector e1, e2, right? Because it's lying in the plane. And if you're rotating something that's lying in the plane of the rotation, you anti-commute. If you're rotating something that's perpendicular to the plane of rotation, you commute. But it's in the plane. It's obviously E0 is in the plane of E1, E0, right? In the bivector defined by, or the plane defined by this bivector, E0 lies in it. So you move this across, but you pick up a minus sign, and therefore this alpha over 2 goes away, and you're just left with minus alpha 2 E1, E0 times E0. Okay, so what is this object? Well, you could leave it that way, but let's blow it up, right? This is hyperbolic cosine alpha 2 minus hyperbolic sine alpha 2. That minus sign comes from this minus sign right here, using Euler's rule for hyperbolic things. And the sine piece keeps what we would call the imaginary part, but it's not really the imaginary, because remember, this thing squares to 1. So it's something slightly different, right? But the point being that this part comes down with the hyperbolic sign. And then, of course, you have E0 on the far right. So then you just do this calculation. We know that alpha 2 is 0.4236. So you put 0.4236 in here, and you use your calculator, and you get 0.10911 E0 minus 0.4364 E1. And that is the vector u. That is the one blade that represents the motion of the bullet with respect to the satellite. And if you square this, you should square this, and you better get 1, right? Because remember, all 4 velocities are supposed to square to 1. So, but when you do square this, remember E1, you take the dot product with itself, right? E1 squares to 1. Squares to, wait a minute, what are we doing? Yeah, minus 1. So that's going to cancel that minus 1 there. In other words, E1 squares to minus 1, right? So this is going to go to, E1 squared is going to be minus 1. But this is minus 0.4364 squared, but it's minus that squared, right? Which means this minus sign goes away when you square this first term, and you end up keeping that minus sign. So it ends up being the square of this. It ends up being the square of this thing, right, minus the square of this thing. And when you do that, it ends up being 1, right? I checked. Okay, so now we have to find the blade, the one blade. Well, it's not really a blade, right? It's, what are we calling it? It's really just a vector, right? It's a vector in the spacetime algebra. The vector in the spacetime algebra that represents this relative vector, which is the velocity of the spaceship relative to the space station. So we calculate its rapidity. That's another, we just do the same thing. Its rapidity is 0.5493, and I calculated gamma to be 1.15. That sounds about right? You know, if you're moving at half the speed of light, your gamma is still not that big. Things are about 15% more intense when you're at half the speed of light. And then beta gamma is which is the hyperbolic sine of that, is 0.5773. And then we do the same thing, the same maneuver, but this time V is going to the positive direction, so we don't have a minus sign there. And therefore, we just get e to the alpha 2, E1, E2, and therefore there's no minus sign here. And this, when you substitute in alpha 2, this should be an alpha, wait a minute, I was calling this alpha 2 up here. So down here, this should be, these guys here should be alpha 1s, right? Should be alpha 1 and alpha 1. And alpha 1. So when you do this calculation, right, you calculate the hyperbolic cosine of 0.5493, the hyperbolic sine of 0.5493, you end up with these numbers here, and just like before, this squares to be positive, that squares to be positive, E0 squares to positive, but E1 squares to negative. So when you do that, you end up with V squared equaling 1. So that checks out. Okay, so from there, now remember, our goal, we need to calculate this thing right here. So let's calculate U dot V first. Well, this is U, right? We calculated U right here, right? So we're going to take this and move it right there. And we just calculated V, which is this. So that goes right there. And we're going to just do the dot product in the usual way. And here we see this first part, the cross terms go away because E0 dot E1 is 0. So only terms that matter are the ones that are direct terms. So we have 1.0911 times 1.1547. Turns out that that is 1.2599 E0 squared. And then the other part is minus 0.4364 times positive 0.5773 E1 squared. So these two multiply together to give you a negative 0.2519, but E1 squared gives you another negative sign. So you end up adding this number to this number, and you get something larger than this number. You get 1.5118. So U dot V is 1.5118. And then U wedge V is just the same two things wedged together. So now the direct terms go away and the cross terms survive. But notice that the first cross term is E0 times E1, 1.0911 times 0.5773, which is 0.6299 E0 E1. And notice I'm using the notation without the wedge there because the geometric product equals the wedge product when you have orthonormal basis vectors. Just a little reminder there. And then the other cross term is minus 0.4364 times 1.1547 E1 E0, and that's this term here. And then we want our blade to be E1 E0, so we flip these two around, pick up a negative sign, and then therefore we take the sum of this and the opposite of the sum of these two, which is minus 1.1338 E1 E0. Okay, so now we want to calculate, finally, we're after U prime, right? The relative U prime, right? And we're expecting that to be negative 0.75. And so, indeed, we can do this calculation. We do minus 1.138 E1 E0 in the numerator, and the denominator gets 1.5118 in the denominator, and you do this division, and you end up with 0.7499, with the minus sign, So you get minus 0.7499, which is, in fact, the minus 0.75 we were shooting for. So this formula it applies for any v and any u, right? It's an easy velocity addition formula. This is the velocity addition formula, or a way of doing velocity addition in this process. And you can work this to recover the actual velocity addition formula of elementary classical relativity. Now, is this easier than what we did over here? Right? Not that one. That was a different version I was planning on using. So you could ask, well, is it easier than this? And that's a bit of a unfair comparison, because here you have to memorize a whole formula. And by the way, this formula only works in one configuration. And that only works in the configuration where everything is moving in one dimension like this, right? And the bullet is moving opposite the spaceship and all that. There's a more general formula, vector formula for sort of arbitrary motions. I think we actually looked at it in one of the earlier parts of this series when we were studying special relativity. And the general one is hard to remember. It's complex, hard to implement. And so arguably the notion, but this statement here, whoops, I keep going back to the one I don't want to use. Yeah, this statement here, right, is always true. It's always true. So if you want to know what the relative velocity is given two known velocities in a frame, you just calculate this, and it'll apply no matter what motion of u is and what the motion of v is. It'll always work. Now, it'll probably be a little more complicated than this, because in this case, we still stuck to one dimension. But, this could have been something e plus e2 plus e3 and plus e2 plus e3 over here. That would have been fine. There would have been no, it wouldn't, the formula is good for all the circumstances. Of course, the general formula in special relativity using the regular vector analysis is also good in all circumstances. But this is so very elegant and simple, and undeniably it's interesting in that regard. And you certainly could set up a computer to do this in a heartbeat, right? Okay, so where have we stopped? So we brokered this last sentence into that long digression that we just had using that real world example, which I think was good. It was a nice exercise. Now, Duran and Lazenby have other things they want to talk about. They talk about momentum, and then they start the section on Lorentz transformations, and they kind of do all the work we've already done. This section on Lorentz transformations just here in order for them to be able to set up the rotor form of Lorentz transformations, which we actually exercised. We actually did this whole exercise. We used these rotors just a moment ago. So we don't really need to go through those Lorentz transformations. We may want to go back and do momentum. What is interesting is they do have their own section on the addition of velocities. And they essentially do it the way we did it. I borrowed from the setup, right? So they said, suppose we are in a frame with basis vectors e1, e0, and we have two objects flying apart with these two different four velocities. And so they, that's where they introduced this negative sign up here, and you have two things flying apart in our reference frame. And the question is how fast do they look like to each other? And here's the formula, right? They're setting up the same thing as we set up, but they stick with the trigonometric form all the way, right? V1, V2, they calculate it as the hyperbolic sine of the sum of the two angles and the hyperbolic cosine of the sum of the two angles. And it's worth seeing how this works. I don't want to belabor it, but let's just quickly look at it. Right, so they start with V1 wedge V2 is going to be e to the alpha E1, E0, E0 wedge e to the minus alpha 2 E1, E0, E0. And you just blow that up, right? You substitute the Euler form here, and you substitute the Euler form here, and then you realize that E0 is 1, right? So that becomes 1, and that becomes 1. So then you just multiply everything out with wedge products, and the wedge product gets buried in the notation E1, E0, because the geometric product, again, of orthogonal vectors is just the wedge product. And then we're going to flip these signs. So we're going to flip the order of the E0 and E1, and we're going to lose the minus sign. and we're going to get the hyperbolic cosine of alpha 1 times hyperbolic sine of alpha 2, hyperbolic cosine of alpha 2, hyperbolic sine of alpha 1. And we know this hyperbolic trigonometric relationship, that this thing here is just, it's the angle sum formula for hyperbolics. And likewise, we calculate v1 dot v2, and we get the same sort of thing, but it is the hyperbolic cosine sum of the two rapidities, alpha 1 and alpha 2. And of course, this one here is a bivector, and this one here is a scalar. Then we just take the ratio of the two, and we get the sine over the cosine, which gives us the sum of the hyperbolic tangent of alpha 1 and alpha 2. And that's what they got right here, right? That's what they got right here. And then by using the hyperbolic tangent sum of angle rule, they recover what looks very close to be the classic angle. They say this recovers the familiar formula. My familiar formula has a plus sign here, right? If the hyperbolic tangent of the rapidity is a velocity, and the hyperbolic tangent of this rapidity is a velocity, right, then I'm expecting the product of the two velocities, but I'm expecting a sum. So somehow a sign kind of wanders in here that's very dependent on this initial setup. So you don't really recover the general formula here because of the way this is set up in a very particular way, so that these become absolute numbers, but the sign is already accounted for. So it's not quite as, it's not the familiar formula for me. It's got a minus sign here, which is a problem. But anyway, that's how they get to it. Now notice they use this weird notation right here in the middle, right? So that is, I wrote that down too so you could see it. The idea is that the wedge product of V1 and V2 is the two-blade part of the geometric product of V1 and V2, right? So they just take, let's just calculate this. Let's calculate V1, V2, and take the blade 2 part. That's also the wedge product that we're after. And so you can do that. You can set that up, and then you can anti-commute E0 and alpha 2, and then you get E alpha 1, E1, E0, E alpha 2, E1, E0, 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 but that of course is 1. And then here you just use the exponential sum rule. And then once you've done that, well, you've got the hyperbolic cosine part, the hyperbolic sine part, but only the hyperbolic sine part is blade 2. So this goes away because you're selecting the bivector piece. So again, you end up with this equals the hyperbolic sine of the sum, right? So that's basically how their notation is working here. It's good to see all these types of notation. But I think that's all for now. There are other interesting examples in here. I'm not sure I'm going to go through any of the others. Just a few to get ourselves exercised and show that special relativity is absolutely just completely sitting there in the geometric algebra. And you can just go through more and more examples. There's no problem in special relativity you can't solve with geometric algebra. Okay, so I'll have a look and see if I want to do another example like this or just move back into the paper next time. But regardless, I will see you next time.